Hi everyone, welcome back. In this video, we're going to be looking at conversions once again, but this time we're going to be looking at mole conversions. All right, so let's go ahead and first talk about what a mole is. A mole is called a chemist's dozen. So just like how a dozen is equal to 12, a mole is equal to a number as well, but instead of that number being 12, it's equal to 6.022 times 10 to the 23rd. Notice that that number has 4 significant figures. So it's been rounded to just 4 significant figures. So why do we need to have a mole? Why can't we just use a dozen for atoms as well? So we know in everyday life, a dozen of anything is visible to our eyes. So a dozen donuts is 12 donuts, and we can see them. A dozen eggs is 12 eggs, and we can easily see them. A dozen atoms, though, is not visible to our eyes. So the dozen amount does not work when we try to relate it to the mole, or sorry, to atoms. But if I use a mole of atoms or carbon atoms, which is rather than 12 of that atom, it's 6.022 times 10 to the 23rd atoms, it's visible to us and we can see it. So whereas the dozen works for things in everyday life that we can see, it is not a good measuring device to use or measuring amount to use for atoms. So instead, we have come up with the mole. Where does the value of the mole come from? Where does this random number 6.022 times 10 to the 23rd come from? So the average mass of one carbon atom, right, if we look here at the bottom on the periodic table, it's 12.01 atomic mass units. If I were to take 1 mole of carbon atoms, that would have a mass of 12.01 grams. So this number here on the periodic table, this bottom number, can actually be used for 2 different things with 2 different units. I can look at it as the average mass of a single atom of that element in units of AMU, or I can use it as the mass in grams of a single mole of that element in units of grams per mole. So although this 6.022 times 10 to the 23rd number seems random, in reality, it allows us to use this bottom number on the periodic table, both in terms of atomic mass unit and grams per mole. So that number at the bottom has 2 different units. Atomic mass unit is the mass of a single atom of that element. So a single atom of carbon on average has a mass of 12.01 AMU, or I can use it for 1 mole of a carbon atom and say 1 mole of carbon atoms has 12.01 grams of mass in it. And we know now that that 1 mole of carbon atoms is made up of 6.022 times 10 to the 23rd atoms. So that's true for all other elements on the periodic table as well. So for example, 1 mole of helium contains 6.022 times 10 to the 23rd atoms, and it weighs 4.00 grams. So this number on the periodic table here at the bottom is the mass of 6.022 times 10 to the 23rd atoms of that element. Same thing with iron. 6.022 times 10 to the 23rd atoms of iron have a mass of 55.85 grams. All right, so let's go ahead and look at some conversions now. If we wanted to convert between dozens and number of a particle versus moles and a number of that particle, how do we do it? So let's first start off with dozens because we're familiar with that. So let's say we wanted to convert 3 dozen atoms to number of atoms. We always start off with what we're given. So we start off with 3 dozen atoms. Remember when we talked about conversions, we said we start off with what we're given. The unit we're trying to get rid of goes on the bottom. So dozen atoms goes on the bottom. number of atoms, which for 1 dozen is 12, goes on top. The dozens cancel. 3 times 12 is 36. So the answer is 36 atoms. Notice that that number has infinite significant figures because dozens can be counted and 36 atoms can be counted. Now let's look at another example where we're going to convert, instead of dozens, we're going to convert moles to number of atoms. Same idea, so now we're going to convert 3.0 moles of atoms to number of atoms. Again, we start off with the 3.0 moles of the atoms, and now we put the moles of atoms in the denominator, just like how we put the dozens here in the denominator. And on top, we put the 6.022 times 10 to the 23rd atoms, right? Because that's equal to 1 mole. These relationships, the top and bottom, have to be equal to each other, the conversions. And then I multiply through. Since 3.0 had only 2 significant figures, my final answer will have just 2 significant figures. Notice the difference between dozens and moles is that with the dozens, my number had infinite significant figures. With moles, my answer does not have infinite significant figures. It's limited by what I was given. And the reason is because the mole is such a large number that in reality, it's not a counting number. We cannot count to the mole. And so its significant figures are limited. All right, so now what we're going to do is we're going to look at the conversion between dozens and moles, or comparing them, but this time we're going to go in reverse. So now we're going to start off with number of atoms and convert it to dozens. On the previous slide, we went from dozens to number of atoms. So now we're going to convert 48 atoms to dozens of atoms. Again, we start off with the 48 atoms. We put number of atoms on the bottom because that's what we're trying to cancel. Dozens of atoms on top because that's what we're trying to get. For every 1 dozen, there are 12 atoms. So then 48 times 1 divided by 12 is 4 dozen atoms. Notice that again, the 4 dozen here has infinite significant figures because we can count dozens. Now let's look at converting number of atoms to moles of atoms. Instead of dozens, we're going to convert to moles. So we start off with what we're given. So we're converting 4.50 times 10 to the 25th atoms to moles. We're going to start off with this many atoms. And then our conversion is, for each 1 mole of atoms, there's 6.022 times 10 to the 23rd atoms. Notice that I put the 6.022 times 10 to the 23rd on the bottom this time, and I put the mole on top. In the previous problem, we had this in reverse. The 6.022 was on top. But because I'm trying to cancel atoms, and I'm trying to get moles as my answer, the moles goes on the top, and the 6.022 times 10 to the 23rd goes on the bottom. So I divide these two by each other. My answer should have 3 significant figures because 4.50 has 3 significant figures. And so remember that moles, their significant figures is determined by how many is given in our problem. All right, so let's look at the roadmap we have so far. We've learned so far to convert between atoms and moles. If we're going from atoms to moles, we divide by 6.022 times 10 to the 23rd, right? Because I'm trying to get moles. The moles will go on top, the atoms on the bottom. And if I'm doing the reverse and I'm going from moles to atoms, then in that case, the 6.022 times 10 to the 23rd goes on top because I'm trying to get atoms. Remember, what we are trying to get goes on top. What we're trying to cancel goes on bottom. All right, so now what we're going to do is we're going to look at conversions between grams and moles. First, we're going to look at converting moles to grams. So we're given that we have 3.50 moles of sodium. How many grams of sodium do we have? So again, we start off with what is given. So we start off with the 3.50 moles of sodium. And this time, as our conversion factor, we are using the bottom number on the periodic table. Remember that number on the periodic table was the mass per 1 mole of that atom. So for sodium, that bottom number on the periodic table is 22.99 grams, and that's per 1 mole. Remember, it's always per 1 mole. The 6.022 times 10 to the 23rd is per 1 mole, and the molar mass is per 1 mole. The moles will go on the bottom because we're trying to cancel moles. They're asking us to find grams, so grams goes on top. These two units cancel. When I multiply this through, I get this answer here, 3 significant figures, because my answer here has 3 significant figures. Now let's look at the reverse. Let's convert grams to moles. So now this time we're given grams. So we have 4.85 grams of potassium, and we're asked to find how many moles of potassium that's equal to. So always kind of think about the answer and think about whether you expect your answer to be maybe more than 1 or less than 1, kind of the ballpark of the answer. I know that 1 mole of potassium from the periodic table has a mass of 39.10 grams. So if you look on the periodic table for potassium, that bottom number is 39.10. So I know that 1 mole is 39.10 grams, which means that my answer should be a lot less than 1 because I have a lot less than 39.10 grams. So we start off again with what we're given. The 39.10 goes on the top, our bottom, the 1 mole goes on top, the grams cancel, and as expected, my answer is less than 1 mole. 3 significant figures here, so my final answer should have 3 significant figures. Okay? So we have now added another conversion to our roadmap. So we first learned how to go from atoms to moles using Avogadro's number, right? We said we use 1 mole for every 6.022 times 10 to the 23rd atoms. And now we've learned to go from moles to grams. To go from moles to grams, we use the periodic table, the atomic mass, that bottom number, as a conversion factor. Remember that conversions are anytime you have one unit over another unit, you can use that as a conversion factor. So here, I would be using the molar mass. Notice for both of those, the mole is always 1. And then in this case, it's always 6.022 times 10 to the 23rd. But in this case, that X represents the bottom number on the periodic table for that element that we're interested in. I can also go in reverse. I can go from grams of A to moles of A. And if I wanted to go from grams of A to moles of A, I use the molar mass again, but I put 1 mole over the mass. And then I do the reciprocal of what I did up here. Avogadro's number on top, mole on bottom, if I wanted to convert to atoms. So this is the roadmap that we have so far. So we can actually go from atoms to grams using mole as the middle, in the middle. Okay, so let's go ahead and do that. Let's convert between grams and number of atoms. So let's say we're told to convert 6.82 times 10 to the 20th lithium atoms to grams of lithium. Again, we start off with what we're given. So we start off with the 6.82 times 10 to the 20th lithium atoms. And then we're going to convert that atoms to moles. And then we're going to go from moles to grams. So we start off with the 6.82, use Avogadro's number to convert to moles, and then use the molar mass of lithium to convert to grams. Again, remember the 1 mole, the 1 goes with the mole always, okay? And then in this case, it's always 6.022 times 10 to the 23rd. In this case, it's always the mass, which is the bottom number from the periodic table. So we start off with what we're given. I'm trying to first convert into moles. So I use Avogadro's number on bottom per 1 mole, right? So these will cancel. That gives me mole. And then rather than just solving this here and then continuing, I'm going to set it all up and then solve it together. So then times the molar mass 6.94 grams per 1 mole. So now the blue line represents that the moles are canceling. And you can see at the end, I'm just left with grams of lithium. So this number divided by this number times this number, 3 significant figures, because that's what my number originally had, what I was given. So 7.86 times 10 to the minus 3 grams of lithium. I highly recommend you try doing this on your own calculator to make sure that you get the same answer, because part of the tricky part of this is to actually plug those numbers into the calculator correctly. Now, we've learned to use this roadmap for atoms, right? Converting atoms to moles to grams. We can actually use this same exact roadmap instead of using atoms, using molecules or compounds. It's the same identical roadmap with the same numbers and conversion factors being used. So I can go from molecules of, in this case, A2B to moles of A2B to grams of A2B. Okay, notice that up here now, rather than saying 6.022 times 10 to the 23rd atoms, I put 6.022 times 10 to the 23rd molecules equals 1 mole. Why? Because in this case, A2B is not an atom, it's a molecule. And then for the molar mass up here, I use the molar mass of A2B. So it would be 2 times the mass of whatever element A is plus the mass of whatever B is. And I can use the same exact conversion factor for molecules, just like how I did for atoms. So let's go ahead and look at some examples. So let's say we're given 5.23 times 10 to the 19 H2O molecules, and we want to convert that to grams of H2O. Notice that it says H2O molecules, not H2O atoms, because H2O is not an atom, it's a molecule, right? I can't refer to it as an atom. Avogadro's number is not just used for an atom. Avogadro's number is that number 6.022 times 10 to the 23rd. It could be used for anything. It could be used for atoms, for molecules, for compounds, for cars, for beads, for rice, anything I want to. In this case, I'm using it for molecules. So we start off with what we're given, right, which is molecules of H2O, and we have to convert molecules into moles using Avogadro's number. And then we're going to go from moles to grams, just like we learned before, using the molar mass. So I start off with what is given, which is the 5.23 times 10 to the 19 molecules of H2O. I'm trying to cancel molecules, so molecules go on bottom. I'm trying to get moles, so moles goes on top. Each 1 mole of water contains 6.022 times 10 to the 23rd water molecules in it. So the molecules cancel. Now I'm going to convert moles of water to grams of water using the molar mass. Where do I get this 18.02 grams from? From the periodic table. Each hydrogen from the table has a mass of 1.01 grams. There's 2 of them, that's 2.02 grams, plus oxygen is 16.00. When we add the 2 hydrogens and the oxygen together, we get 18.02. So water has a molar mass of 18.02 grams for every 1 mole. I put the grams on top because that's what I'm trying to get, right? It's telling me to find grams of water. I'm trying to cancel moles. Moles goes on bottom. Remember that the mole is always 1. So the number from the periodic table goes on top. I divide and multiply through. My final answer should just have 3 significant figures because I was given 3 significant figures up here. All right, so now what we're going to look at is converting between moles and number of constituent elements. So let's start off with something we're familiar with. So let's look at an example here where we have 2.5 dozen kids in a kindergarten class, and each child in the class has 8 crayons. And we want to know how many dozen crayons there are altogether. Notice that in this problem, rather than converting dozens of kids to number of kids, okay, and then to number of crayons, and then dozens of crayons, I can just go straight from dozens of kids to dozens of crayons in one step. So I can just go straight in one step using the conversion that 8 dozen crayons per 1 dozen kids, right? So if each kid has 8 crayons, then each dozen kids has 8 dozen crayons. So I start off with 2.5 dozen kids. I put 8 dozen on top, 1 dozen on bottom, and when I multiply through, I get 20 dozen crayons as my final answer. So I did this all in one step, going from dozen to dozen. We can do the same thing between moles of compound and moles of its constituent element. So let's say I have 3.5 moles of H2O and I want to know how many moles of hydrogen I have. Notice that from this H2O molecule here, I can see that one H2O contains 2 hydrogens in it. So to convert, I can just go straight from moles of H2O to moles of hydrogen using the conversion that in our example, like we saw, 2 moles of hydrogen for every 1 mole of water. So I start off with the 3.5 moles of H2O. For every 1 mole of H2O, I have 2 moles of hydrogen, right? So the subscript here can be a mole-to-mole relationship or a number-to-number relationship. And then I multiply through and I get 7 moles of hydrogen or 7.0 moles of hydrogen as my final answer. So now we can actually expand the roadmap that we originally came up with. Originally, we started off with atoms of A, and we learned to convert it to moles of A and to grams of A. So I've just kind of turned what we learned sideways. We also learned that we could apply the same exact relationship here, instead of to atoms, to molecules and compounds. So we can go from compounds to moles, right, using Avogadro's number, and then mole to gram using molar mass. And then what we just learned is that we can also go from moles of the compound to moles of the constituent element in just one step using the actual chemical formula as a conversion factor, right? There's 2 A's for every 1 A2B. So if I connect all this, you can see that I can go from compounds to elements by using the mole-to-mole conversion here as a bridge to connect the two. So if I were given number of compounds and I wanted to convert to grams of the constituent element, which is down here, I would just take this relationship here. If I were given grams of compound and I wanted to know grams of the constituent element, I go from grams of compound to moles, mole to mole conversion, mole to gram. So I can always go from compounds to elements using the mole to mole conversion here as the bridge to connect the two. So wherever I am here, my goal should be to convert to moles. If I start off here, I go to moles. If I start off here, I go to moles so that I can cross the bridge. If I start here, I go to moles so that I can cross the bridge. And if I start down here, I go to moles so that I can cross the bridge. So your goal should always be, if you're not given moles, to convert into moles so that you can use this road, this bridge here, as a conversion factor. Okay, so now we're going to look at an example together where we're going to try to find how many atoms of oxygen are present in 24.6 grams of KNO3. So the first thing we need to do is come up with the roadmap that we're going to follow to answer this question. So from the map that we have, what we're going to do is look at where we start. So we're given 24.6 grams of KNO3, so we're given grams of our compound. So we're starting off down here at the grams of compound. We're told to find the number of atoms of oxygen, so we're going to end up here at atoms of the constituent compound. So this is where we're trying to end up. So we have to go from grams of KNO3 to moles of KNO3 using the molar mass of KNO3. And then we're going to go from moles of KNO3 to moles of oxygen using the chemical formula as a conversion factor. And then in the last step, we're going to go from moles of oxygen to atoms of oxygen using the Avogadro's number as a conversion factor. So let's go ahead and write the roadmap. So we're going to go from grams of KNO3, convert to moles of KNO3 using the molar mass, right? Then we'll go from moles of KNO3, we'll cross over the bridge to moles of oxygen, and then we're going to go from moles of oxygen to atoms of oxygen in the last step. Okay, so we start off with what we're given, which is 24.6 grams of KNO3. So that's what we start off with. To convert grams of KNO3 to moles of KNO3, I use the molar mass of KNO3. I'm trying to cancel grams, so grams goes on bottom, right? Remember we learned that before, that the unit you're trying to cancel goes on the opposite end. I'm trying to get moles of KNO3, so moles of KNO3 goes on top. And what we've learned so far is that the mole gets the 1. So here, I put a 1 for the mole. For the grams of KNO3, I have to use the molar mass of KNO3 from the periodic table. K has a mass of 39.10 plus 14.01 for the nitrogen, plus 3 times 16.00 for the oxygen. All of that added together gives us 101.10 grams. And you can see here that I've canceled the grams of KNO3. Now what I need to do is go from moles of KNO3 to moles of oxygen. I'm trying to cancel KNO3, so moles of KNO3 goes on bottom. I'm trying to get moles of oxygen, so moles of oxygen goes on top. As a conversion factor in this case, I'm using the chemical formula KNO3. You can see that for every 1 KNO3, there are 3 oxygens, which means that for every 1 mole of KNO3, there are 3 moles of oxygen. And so now the moles of KNO3 cancel. And then in this last step, I need to convert from moles of oxygen to atoms of oxygen. The moles goes on bottom. The atoms goes on top. And like we said, the mole is going to always get the 1 for both the Avogadro's number, right, the 6.022 times 10 to the 23rd, and for the molar mass. So on top, we put the 6.022 times 10 to the 23rd. So you can see now that the moles here cancel, the moles of oxygen, and then I will be left with the atoms of oxygen. And when I multiply all this through, I get to 3 significant figures, right? Because 24.6 has 3 significant figures. I get 4.40 times 10 to the 23rd power. So this is how many atoms of oxygen we have present. And that will be my final answer. Okay, so just a quick recap of what we learned so far. The most important thing to solve these problems is to come up with the roadmap. What we learned about the roadmap is that we do compound, right, atom, and for the compound, we can start off at the number of compounds. We can convert that to moles of the compound, and we can convert that to grams of compound, right? And vice versa. And we learn to do the same thing for the atoms. We can go from number of atoms, convert to moles of the atoms using Avogadro's number, and we can go from moles to grams using the molar mass. This is compound. And then we learned to go from mole to mole conversion here using the chemical formula, right? So let's go ahead and look at this. So to go from number of compounds to mole, here we use Avogadro's number, right? Remember, Avogadro's number is 6.022 times 10 to the 23rd per 1 mole, or you need to use the reciprocal of it. To go from moles to grams, we use molar mass, right, which is the grams per mole from the periodic table. To cross over the bridge, we use our chemical formula to see how many of that atom is in the formula. And then again here, to go from moles to atoms, we use the 6.022 times 10 to the 23rd, right, per 1 mole. And to go from moles to grams, we use the molar mass, which is the grams per 1 mole. Remember that this is all 1 mole. Okay, so if you can come up with this on your own, then you can start anywhere on here. You can start anywhere on here, depending on what you're given, and you can work your way around. You might be given number of atoms and asked to find grams of compound, or number of compounds and asked to find number of atoms, but you just always remember having to cross over this bridge here. So here are some practice problems for you to attempt on your own, and then on the next slide, you'll be given the answers. So you can just press pause, complete these on your own, and then check your answer on the following page. And here are the answers to these questions that you were given on the last slide.